Okay, so we'll look at the types of machines. Types of machines. The first one is the lever. Second is the pulley. The pulley is also known as the block and tackle pulley system. The third one is the inclined plane. Fourth is the screw and screw gauge. Fifth is the wedge. Six is the wheel and axle. Seven is the gear wheels. So we'll start with the lever. I think we have about 7 machines here. We'll start with the lever, and each of them have their separate explanations and calculations as well. So let's look at the lever system. The lever. Okay, the lever, it consists of a stiff bar or rigid rod supported at the fulcrum or pivot about which it can rotate. An effort E applied at one point of the lever lifts a load L at some other point. So this is the lever. This is the rigid rod, a rigid horizontal rod. At this point you have the fulcrum or the pivots about which it can rotate. So this is the effort applied here. Distance moved by effort is A with respect to this pivot, and this is the load. This vertical line here is the load. Distance moved by load is B with respect to the pivot here. Okay, so we apply the principle of moments. That small triangle you see is the balance point or the fulcrum, which is also known as the pivot. So applying the principle of moments. So you see, applying the principle of moments. Applying the principle of moment, we can take this one going anti-clockwise with respect to this pivot, and we'll take this other one going clockwise with respect to the pivots. Okay, alright, so that is it. So this will go clockwise with respect to this pivot, this will go anti-clockwise with respect to the pivot. So I'll say anti-clockwise moment. Anti-clockwise moment is equals to clockwise moment. Okay, so the anti-clockwise moment now will be this force times the perpendicular distance with respect to the pivots. So we are taking moment at the pivots. So say take moment at the pivots. The pivot is the balance point. That is small triangle. So the anti-clockwise moment now is this force times the perpendicular distance A. That is effort times distance moved by effort. The clockwise moment is the load times the distance moved by load with respect to this pivot. That is load times distance moved by load is B. Now if I change this linear equation to a fraction, I will be having load over effort will be equal to A over small b. Okay, and we know that A is the distance moved by effort, and small b here is the distance moved by the load. From this diagram, this is the load, and distance moved by the load is small b. This is the effort, and distance moved by the effort is small a. Okay, so we are arriving at something like this. Load over effort equals to distance moved by effort over distance moved by load. Now we know that mechanical advantage is this and velocity ratio is this. Okay, so we know that mechanical advantage is load over effort, velocity ratio is distance moved by effort over distance moved by load. Alright, you say but my mechanical advantage is load over effort and velocity ratio is A over B, that is distance moved by effort over distance moved by load. Okay, so it implies that for a lever system, lever system of the form L over E equals to A over B, that my mechanical advantage is equivalent to the velocity ratio. Okay, as from that diagram, everything we have solved there, and we took the anti-clockwise moment equals to clockwise moment. Finally, we arrived at mechanical advantage equals to velocity ratio. Why? Distance moved by effort over distance moved by load is this. Load over effort is this. Alright? Alright, so we'll consider the types of lever. The types of lever, we have the first order lever, the second order lever, and the third order lever. First order lever, second order lever, and third order lever. These are the three types of lever. Okay, now look at the first order lever. In this lever, the fulcrum is between the effort and the load. Fulcrum is between the effort and the load. Examples of first order lever are the crowbar, a pair of scissors or pincers, claw hammer, and pliers. The velocity ratio of a first order lever is usually greater than 1, but could be less or equal to 1. That is, velocity ratio is greater than 1 or velocity ratio is less than equal to 1. Mathematically you have velocity ratio VRO is greater than 1, or VRE is less than equal to 1 for a lever. Okay. Now this is it. This is a diagram of a first order lever. First order lever shows us that the fulcrum is always in between the effort and the load. Okay, the figure shows us a first order lever. It shows us that the fulcrum is always between the effort and the load. Okay, so we'll take note of the examples of first order lever. We have the crowbar, a pair of scissors, pincers, then claw hammer or pliers, and and we must note that the fulcrum is always between the effort and the load. So the fulcrum is always between the effort and the load. Okay. All right, let's look at the first one. The first one is the pliers. The pliers, and look at this. We see the effort is applied here. The load is at this other point. This is the load, and then this is the fulcrum. The fulcrum is this screw nail at the middle. So the fulcrum is always between the load and the effort. Now let's assume I'm trying to cut a piece of wire. Okay, so that's the load. The piece of wire is the load, and then this screw nail in the middle is the fulcrum, and effort is applied at the handle. Okay, so the pliers is a perfect example of a first order lever. Okay, now let's look at the next one, a crowbar. Let's look at the next figure, a crowbar. This is a crowbar. You see that the load is at this point, and then this is the fulcrum. It's just like a wedge, and then the effort. Now this is the crowbar. This instrument is the crowbar. Now when I apply this effort here, when I press this thing like this, going down this way, what happens? There will be an effective force that will lift this block upwards. So as I apply effort down this way, pushing it downwards, applying effort here, there will be an effective force that will cause this load to lift upwards. So we see that the principle of moment is actually applied here. Okay, so this will be going kind of clockwise, and this one will be anti-clockwise of that nature. Now you see that the fulcrum is this wedge that is placed here in the middle. So this is a perfect example of a first order lever. The fulcrum must always be between the load and the effort. Effort is applied at the handle. The fulcrum must be between the load and the effort. Okay, so a crowbar is a perfect example of a first order lever. The first example there was the pliers. Okay, take note of it. You see that the fulcrum is in between the load and the effort as well. Same as the crowbar, fulcrum is always between the load and the effort. The next example is a pair of scissors. A pair of scissors, we see that the two handles here, effort is applied on this handle, and then the fulcrum is this nail at the middle, and the load now is this stuff over there. It might be a little object, maybe a nail, a piece of wire or paper or cloth. This little object over there is the load. Now you see that the fulcrum is always at the middle. On application of effort, what happens? This thing will join together and cut that object. So we see the load there is this little object, the fulcrum is this nail in the middle, and the effort is over there. So for a first order lever, the fulcrum must always be between the load and the effort. The fulcrum is always in the middle. All right, take note of that. Now let's go over to the second order lever. Let's look at the second order lever. Let's look at the second order lever. Quickly, let's consider the second order lever. All right, we'll look at the second order lever. In this lever, the load is between the effort and the fulcrum or pivot. Examples of second order levers are wheelbarrow and nutcrackers. Okay, now this is a diagram of the second order lever. The load is between the fulcrum and the effort. So we see that the load is between the fulcrum and the effort E. Right? This is a second order lever. Now the mechanical advantage and velocity ratio are always greater than 1. That is, mechanical advantage greater than 1, velocity ratio is greater than 1 for a second order lever. Now remember I told you that in the first order lever, the fulcrum is between the load and the effort. Now, but in a second order lever, the load is between the fulcrum and the effort. That's for second order lever. Load is always in the middle. Load is always in the middle. It's between the fulcrum and the effort. But for a first order lever, the fulcrum is in the middle. Okay, so take note. So the load is always in the middle in the second order lever. Now, the examples are, you have wheelbarrow and nutcracker. So let's look at those examples. Let's look at those examples quickly. Let's look at those examples. This is a diagram. Take note of the diagram for a second order lever. Okay, so this one now shows us the diagram of a wheelbarrow. And you see the effort is applied at the handle. And then this is the load over there in the middle. And the fulcrum is there at the tire. The position where the tire is meant to be. Okay, so this is the wheelbarrow. And there, that is it. Wheelbarrow is a perfect example of a second order lever because the load is always at the middle between the fulcrum and the effort. Then you come to the nutcracker. The nutcracker as well, the load, this is the load here at the middle. This load, you are trying to crack this nut. The nut now is the load. And this screw nail here shows you the fulcrum. The screw nail is the balance point, is the fulcrum. The moment you disassemble this screw nail, the moment you remove the screw nail, you have scattered the nutcracker. So the screw nail keeps the nutcracker in position, keeps it in a firm equilibrium position. That's the essence of this screw nail. It is called the fulcrum. Now the load, the effort is applied at the handle. The effort is applied at the handle. When you press this thing, you'll be able to crack this nut. The nut is the load that stays in the middle. So the nutcracker is a perfect example of a second order lever because the load always stays in between the fulcrum and the effort. So that is the nutcracker. And then for the wheelbarrow, you see that the load is here, staying in the middle. It is in between the fulcrum and the effort over there. Okay, so that is it. The load is always between the fulcrum and the effort. That's for the wheelbarrow. Alright, now let's go over to the third order lever. The third order lever, quickly. The third order lever. In this lever, the effort is between the load and the fulcrum. Examples of third order lever are forceps, tongs, and forearm. The mechanical advantage and velocity ratio are less than 1. Means that mechanical advantage is less than 1 mathematically. Velocity ratio is also less than 1 mathematically. Now this is the diagram of the third order lever. You see that the effort is in the middle. It is in between the fulcrum and the load. The effort lies between the fulcrum and the load, or you see between the load and the fulcrum. This is the effort right there at the middle. So it means that for a first order lever, the fulcrum is in the middle. For a second order lever, the load is in the middle. And for a third order lever, the effort lies in the middle. So effort is in between the fulcrum and the load. That's the third order lever. This diagram shows you the third order lever. So this diagram shows us the third order lever. The third order lever. Okay. The third order lever. Alright. Now let's go back to the examples. The examples are forceps, tongs, and forearm. Alright, quickly let's look at the examples. Over here we have the forearm, and down here we have the forceps. And observe the way the effort, fulcrum, and load is positioned. See the effort here, positioned in the middle. This is a load, and over here is the fulcrum. So I'll apply my effort here. I will put my hand here, press this thing, and then the moment I apply effort here, by pressing this properly, now I'll be able to grab this load. So I'll cleave to it. Over here at the middle, I'll cleave to it, and then I grab the load. That is how the forceps work. And this curved portion here is the fulcrum, which is the balance point. That's the knife edge. The balance point is the fulcrum at the edge over there. Now the effort is applied in the middle. All right. Now when I press it, I'll be able to carry this load up. Okay. Now let's look at the forearm. the forearm. Let's consider the forearm. You see that the effort is at the middle here. At the middle, that is this point, your elbow, this point between the this portion of the hand and this one. This is the elbow at this point here. So the effort is applied here, specifically at the elbow, this middle side, and this is the fulcrum at this portion of your shoulder, fulcrum, and over here at your arm, this portion of your arm is the load. So this is the forearm. The forearm now, the analysis is showing you that the effort is at the elbow, the fulcrum is at the shoulder, and then the load is the arm. So you see the effort is at the middle side. You see the effort at the middle. So the effort is between the load and the fulcrum. Okay, that's for the forearm. Okay, so take note of the diagram. For a third order lever, the effort is always between the load and the fulcrum. Effort is always between the load and the fulcrum. Okay, this is a forceps, and this one is the forearm. Effort is always between the load and the fulcrum. Alright, let's look at this question. It says, which of the following levers has the greatest mechanical advantage? Which of the following levers has the greatest mechanical advantage? Okay, this is the first one. The first one here, we have dimension 3 cm and 1 centimeter. This is the load and this is the effort. Okay. The second one, we have dimensions 2 cm and 2 centimeter. This is load and this is effort. So distance moved by load is 2, distance moved by effort is 2. For this other one, distance moved by load is 3, distance moved by effort is 1. Now let's look at the third option. Distance moved by load is 1 cm, and this is the load. Distance moved by the effort is 3 cm. This is the effort. This is the pivot. This one there is the pivot or the fulcrum. That's this one there. Okay. Now distance moved by the load is 2 cm. The distance moved by the effort will be 2 plus 2. That is this. That's distance from here to here. Okay. That's the pivot over there. Alright. So I'll say consider option A. Consider option A. I'll draw it out. This is my load, and then this is my effort. This is the effort E. Okay, and then this is a little the triangle there shows you the fulcrum or the pivot. This is 1 centimeter, and this other one is 3 cm. This is 3 centimeter. Okay. Now we'll take moment with respect to this pivot, and we'll see that the load will move this way with respect to the pivot, and the effort will go like this with respect to the pivot. Okay, so you're taking moment with respect to the pivot. So taking moment with respect to pivots. So with the principle of moment now, it tells us that anti-clockwise moment is equals to clockwise moment. Okay, so I said the anti-clockwise moment is equals to clockwise moment. Anti-clockwise moment now is this load times the distance moved by load. As this one times this distance. That's the perpendicular distance, 3 cm. That will be L times 3. The clockwise moment is this effort times this distance, 1. E times 1. Okay. So now it means that load over effort will be equals to 1 over 3. Okay. That is it. This times this times this is this. And this times 1 is this. Alright. Okay. So now I have that my load over effort will be equal to 1 divided by 3 will give me 0.33. Okay, I say but mechanical advantage is equals to load over effort. So therefore the mechanical advantage is 0.33. This is for option A. Option A, my mechanical advantage is 0.33. Now let's look at the next option, option B. Okay, the next option, option B. Quickly, let's look at option B. And I'll be having to consider option B. Consider option B. Okay, this is the load, and then this is the effort E, and the fulcrum is at the middle. Distance from here to here is 2 cm. From here to here is 2 cm as well. Okay, so I then take moment with respect to the pivots. That's okay, so taking moment with respect to pivots. Taking moment with respect to the pivots, you say the anti-clockwise moment. Anti-clockwise moment is equal to clockwise moment. Okay, so anti-clockwise moment equals to clockwise moment, and I'll be having okay, so the anti-clockwise moment is this times this distance, that is L times 2, and the clockwise moment is E times 2. This times this one times this one. Okay, so my load now, I have load over effort is equals to 2 over 2, which is 1, right? So when I convert this one out to a fraction, I have this. That means my mechanical advantage is equals to 1. The mechanical advantage is load over effort, which is 1. So in this case, say MA is equals to 1, right? Mechanical advantage is 1. Mechanical advantage is 1. Alright, so let's consider option C. Consider option C. Distance from here to here is 1, and here to here is 3. So I'll still take moment with respect to this pivot. This will go clockwise, this one will go anti-clockwise. So say anti-clockwise moment equals to clockwise moment. So the anti-clockwise moment now is the load times distance 1, that's from here to here is 1. And this other one now, clockwise, will be effort times this distance 3, that's E times 3. So load over effort will be equals to 3 over 1. Okay, that's effort times this times this, E times 3 is this, and L times 1 we give it this. I just converted it to fraction. Convert this linear equation to fraction is this. So that means that this is equals to 3. Therefore, mechanical advantage is 3. You know, MA is equals to load over effort, which means that mechanical advantage is 3 in this case. Mechanical advantage in this case is 3. Right, so let's look at the next case. Look at option D. Let's consider option D. So in option C, we solved and we got the mechanical advantage as 3. In option A, we had the mechanical advantage as 0.33. In option B, we had the mechanical advantage as 1. So let's look at option D and see what we'll get. Okay, consider option D. Consider option D. This is what we're having. I'll take moment with respect to the pivot. This one will go clockwise until it gets to this point, while the effort will go anti-clockwise. To go anti-clockwise until it gets to this point. Okay, so taking moment with respect to pivots, you see clockwise or anti-clockwise moment. Let's take clockwise first. Clockwise moment equals anti-clockwise moment. Okay, so you say clockwise moment equals anti-clockwise. Now the clockwise moment is this, that is this load times this distance, that is L times 2, and the anti-clockwise moment will be this effort times distance from here to here. Okay, that is effort E multiplied by 2 plus 2. Alright, as this effort times distance from here to here is 2 plus 2. While the load is this, distance from here to here is just 2. So clockwise moment is this times this, which is force times the perpendicular distance, which is L times 2, while the clockwise moment will be clockwise moment is this, clockwise is this, that is this load times this distance. Anti-clockwise is going anti-clockwise like this, effort times distance from here to here, which is 4. Okay, so this times this, and then this distance times this one is clockwise. Alright, so take note. So that is L times 2, which is 2L, is equals to E times 4. That is 2L is equals to 4E. Okay. Alright, so that means that L over E will be equals to 4 over 2. Alright, so 2 here, 1, 2 into this is 2, which is 2. So therefore, my mechanical advantage, which is equals to load over effort, is equals to 2. Alright, so in this case, my mechanical advantage is 2. So which of them has the greatest mechanical advantage? Option A gave us a mechanical advantage of 0.33. Option B gave us a mechanical advantage of 1. Option C gave us a mechanical advantage of 3. Option C gave us a mechanical advantage of 3. And then option D gave us a mechanical advantage of 2. Okay, so which of them do you think is the answer? The answer is option C. So which of the following levers has the greatest mechanical advantage? The answer is option C. Option C has the greatest mechanical advantage. Because it gave us a mechanical advantage of 3. This one gave us a mechanical advantage of 0.3. This gave us a mechanical advantage of 1. This one gave us a mechanical advantage of 3. And this has a mechanical advantage of 2. So you observe that the one with the greatest mechanical advantage is option C. Right? So the one with the greatest mechanical advantage. So which of the following levers has the greatest mechanical advantage? So you observe option A is mechanical advantage is 0.3. Option B, mechanical advantage is 1. Option C, mechanical advantage is 3. And option D, mechanical advantage is 2. So we have observed that the one with the greatest mechanical advantage is option C, because it has a mechanical advantage of 3. Alright, it has a mechanical advantage of 3. Alright, okay, so we'll stop here for today, and when next we meet, we'll continue with calculations on the lever. When we are done with calculations on lever, we'll go over to pulley system, and after that we'll continue with inclined plane until we get to the gear system. Alright, okay, this is all the solvings we did. Please, whenever we are solving, ensure that you have a pen and a book and you are taking down notes. Okay, please ensure you are studying as well. You are taking down notes so you can go back and read it and study it properly for your exams. Alright, please ensure you have a note and a pen. Okay, so we'll stop here for today. Thank you. God bless you. Thank you.